So when Bohr began looking at the atom, there were a few prevailing theories about the atom. At first, everyone was looking at the idea of the atom just being this pudding of positives and negative charges floating about. And that quickly became obsolete when Rutherford did his Goldfold experiment, and he said all of the protons are all in the middle, they're all tightly bound to each other, and the electrons are outside the nucleus. So that was a great theory, and everyone was starting to go with it, and then they began to look at those electrons and say something isn't right with the electrons. At the time, they only had classical mechanics, which is this is Newton, and the apple falling from the tree. It's gravity and how it interacts with objects that we see and touch, things like that. And classical mechanics started to not make sense with the atom. And there's actually a whole new field of physics that began to develop called quantum mechanics, which you'll hear about later. But classical physics started to not make sense. First of all, electrons, if you look at them as charged particles, which they are, they're negative, and if they're accelerating, this is one of the physics things, is they should be producing radiation. And of course, when you put them in these electrotubes, you can see color, so that's kind of like radiation coming off, not harmful radiation. But then if they're just sitting there, the tubes don't have any color, they're not producing radiation. So why is it that happens? They should always be producing radiation. And then the second thing, and this is the biggest thing, is that the negative charge particle, if it's moving in a circle, it should be attracted to that nucleus and it should crash into it and destroy the atom. So those are kind of some big problems. Bohr is looking at a series of these glowing tubes, which we already said are broken. Your eye combines the different wavelengths together to make one kind of a color, but this is actually many wavelengths, and all of them are different. It doesn't have to be 4 like hydrogen. It could be all different amounts. But you've already learned that different wavelengths means that there are different energy. So one wavelength is going to have a different energy value than a different wavelength, which will have a different energy value. So they have different energies coming off. Yet every time you hook it up, it's always the exact same wavelengths for each type of element. So, the elements are different from each other, but every single time it's always the same. Specific amounts. And Bohr was looking at this and he said, all right, this is like a summarization of some of the wavelengths. So he was looking at hydrogens and he began doing some calculations. And he said, what if the electrons can only have discrete, specific amounts of energy moving around the atom? Moving around the nucleus. So he began placing electrons. Well, and of course, hydrogen was the one he was looking at. There was only one hydrogen electron. He said, well, what if it has to have a certain energy at this position and a different energy at this position? And here's the key thing that he used to prove this theory, is he started measuring what he thought would be different spacings between energy levels, and the difference between what he calculated for the electrons turned out to match with each of these wavelengths that you got every time you stuck something in those spectrometers. So you would end up with this wavelength, which is a certain amount of energy, this wavelength, and he matched that up with how far an electron would have to change energies to jump, but from one position to another. So the Bohr model is this idea of a positive center nucleus, and then the electrons have these orbits, and that they're only in specific energy orbits, and that they can't be anywhere between the orbits. You can't be at platform 9. You can be at platform 9, you can be at platform 10, but you can't be at platform 9 3/4.